Okay, so previously what we did was we found the definition of the characteristic function, which I'll quickly write down. And what this is, if we can remember, is the Fourier transform of the probability distribution of the amount of heat exchanged between our system and environment. So if we imagine we've got our quantum system and it's surrounded by some environment, the entire thing is closed, but the system is open. It exchanges energy and information with the environment, and we're interested in the heat that is exchanged between the two. And in the previous video, what we found was that there does not exist a heat operator, which means that we cannot measure any emission operator directly to find this heat. And instead we have to use this 2-point measurement protocol where we choose an operator that we can measure, in this case the Bath Hamiltonian, HB. And we measure it at 2 different times, and then we take the difference between the outcomes of those measurements that we get, and we use that to define heat. So heat is essentially the change in the expectation value of the Bath Hamiltonian at 2 different times. So let's say at time t and at time 0. And because these 2 measurements are going to be random, as all measurements are in quantum mechanics, then Q is a stochastic quantity, and that's why we need to define it with a probability distribution. And in the previous video, we found that the probability distribution is quite hard to find, but its Fourier transform, which is this characteristic function here, is easier to find. So what we're going to do is find the characteristic function and then take the inverse Fourier transform to get back to the probability distribution which we want. So the main point of this work is to use something called the reaction coordinate mapping. In the context of building probability distributions for heat. And the way that we're going to do this is to apply the reaction coordinate mapping to the 2 Bath Hamiltonians here and here. So let's quickly think about what the reaction coordinate mapping is. So I'm going to draw the little diagram of our system and the environment slightly differently, but it essentially is the same thing. So here we've got our system and here we've got our environment, and instead of having the system encompassed inside the environment as we've had before, I'm just going to draw a line between them, and this line just represents the fact that they're interacting. So as before, the system would be described by some system Hamiltonian. The environment, or the bath, I'm using these terms interchangeably, will be defined by its environment, and then this line represents the interaction between the 2. And then we sum all these together and we get the total Hamiltonian. So what the reaction coordinate mapping does is it takes this picture, and we're going to take a part of the environment out and leave the rest of it there. So I'm going to have a system, and it's going to be interacting with a small part of the environment, which then itself interacts with the rest. And this little thing here that we've taken out of the environment gets called the reaction coordinate, or the RC. So we've still got our system, we've got this RC, and then the reaction coordinate now interacts with the rest of the bath, which we call the residual bath, or RB. So what we've now got is we've gone from a picture where we've got a system interacting with an environment, a large environment with many or infinite degrees of freedom, to now we've got the system interacting with one mode from the environment, which itself interacts with the rest of the environment, which is still infinite because we've just taken 1 away from infinity, so that's still infinity. Why do we do this? Well, we do this in situations where the system is coupled strongly to the environment and where there are no parameters that are small enough for us to rotate with a unitary transformation such that the interaction can be perturbed about one of these small parameters. And an example of that we could do is the Polaron transformation. So we use the reaction coordinate mapping in situations where there are no small parameters that we can use to use perturbation theory. So essentially we go from a picture where we've got a system strongly coupled to a large infinite environment to a picture where we've got a system strongly coupled to a single mode of the environment, which is then weakly coupled to the rest of the infinite bath. And then essentially what we do is we just say, okay, let's just treat the system and the reaction coordinate exactly, and then we'll treat the rest of the bath using perturbation theory. So why are we using the reaction coordinate mapping to define heat? Well, let's think. We've now got a situation where we've kind of got two different baths. We've got this one here, which we'll call the full bath, and then we've got this one here, which we'll call the residual bath. And our question that we're trying to ask is which Hamiltonian, the full bath or the residual bath, is going to be the best one to use to define heat. So is it changes in the full bath or is it changes in the residual bath? And that's the main topic of this work that we're trying to solve. Okay, so let's be a little bit more rigorous about what this reaction coordinate mapping is actually going to do. So we're going to take our bath Hamiltonian and we're going to apply some unitary operator R that performs the mapping. And what's that going to do? Well, it's going to transform the bath into the reaction coordinate, the residual bath, that should be a B, and their interaction, which I'll just call V. And this mapping is done in such a way that this V is small. So basically the interaction between the RC and the residual bath, this is going to be weak right here, which is good because then we can just reframe our problem such that we care about the system and the reaction coordinate, and then we treat the rest of the bath with regular weak coupling Born-Markov approximations. Okay, so what I'm going to do now is insert the identity into the characteristic function, and I'm going to write it as R dagger R. And then we will, so I should have another one there. We will see why I'm doing this in a second. And basically all I'm doing is multiplying a number by 1. So nothing is actually changing. We're essentially just changing our point of view of the problem. That's the way I think about it. We're basically just looking at it from a slightly different angle, and then that's going to help us get to where we want to be. Is that everything? I'm missing. Okay, so I'm missing the step. So let's have another one, and finally U dagger of T. Nice. So now I'm going to use the fact that R times e to the I chi hb times R dagger is equal to this. We can just take those R's up into the exponential. You can see that if you just write the exponential as an infinite sum, and then you'll notice that when you sandwich the thing inside the R's and R daggers, the R's and R daggers can go inside the sum. And then from the previous slide, we know that this is going to equal the reaction coordinate plus the residual bath plus their weak interaction. So this will be the same as this with a minus sign as well. And then let's think about what happens to the unitaries, the time dynamics. Again, because the time evolution is an exponential of this form, we can just take the R's and R daggers into the exponential. And one thing that I forgot to mention about the reaction coordinate mapping is that it leaves the total Hamiltonian invariant. So I'll just write this as minus I h total with a tilde on top times the time. And this is basically just telling us that it's the same Hamiltonian, but we've written it in a slightly different way. So now let's look at what our characteristic function looks like after we perform the reaction coordinate mapping. I'm also going to use the cyclic property of the trace and move the R dagger that was at the front to the back. And then I'm going to write the unitary with a tilde to remind us that the Hamiltonian inside the unitary time evolution has been reaction coordinate mapped. And again, same as the first time, but with the minus sign. Oops, that should be RC plus HRB plus V. And then rho naught bar tilde is just going to be the initial state where we've performed the first measurement and averaged over all the possible outcomes, then also mapped using the reaction coordinate. So just a bit of more compact notation. And finally, we will have U dagger tilde of T. And is that everything? I apologize, there actually isn't an R dagger. I thought there was going to be an R dagger left here, but there isn't, which is good. It gets absorbed into this U dagger tilde of T.